Welcome back to the course of Applied Elasticity. In today's lecture, we are going to talk about the different elasticity theorems. In the previous lecture, we had discussion on the field equations of elasticity, and then we had discussed about the solution approach for both displacement boundary value problem and stress boundary value problems for the elasticity. Now, just to have a quick recap of elasticity formulation for infinitesimally small linear elastic deformation problems, we are having 15 field equations of elasticity. First three are the equilibrium equations, then we have 6 strain displacement relation or 6 strain compatibility relations, then we have 6 constitutive relations. The constitutive relations relate the stress components with the strain component, and these form of constitutive relations are valid only for the homogeneous linear elastic isotropic solids involving two constants, two material constants lambda and mu. They are known as Lamé constants. Now, in between strain displacement and strain compatibility, either one set of 6 equations we need to use depending on out of strain components and displacement components which one is known and which one we need to determine. For all this equation, I and j can take values of 1, 2 and 3. Now, based on the boundary conditions which are required to solve the equilibrium equations, because equilibrium equations are differential equations, we must have some boundary conditions for solving the equilibrium equation. Now, depending on the type of the boundary conditions which can be prescribed either on the displacement or on the tractions or stresses, based on that boundary conditions are classified into two categories. The first one is displacement boundary condition, which is prescribed on the surface boundary displacements, and the second type is traction boundary condition, for which the surface traction values are prescribed on the boundary surface. Now, depending on that, we can have two type of formulations. For the displacement boundary value problems, the expression or the equation is given like this: mu times Laplacian of u plus lambda plus mu times gradient of divergence of u plus b equals to 0. This is called Lamé-Navier equation for displacement boundary value problems. Instead of displacement, if the boundary conditions are prescribed over the stresses or over the tractions, for that case we have stress based formulation of elasticity, and the corresponding governing equation is given by Laplacian of sigma plus 1 by 1 plus nu times gradient of trace of sigma is equals to minus nu times nu divided by 1 plus nu I divergence of b, where I is identity tensor, minus of within bracket gradient of b plus transpose of gradient of b. This equation is called Beltrami-Mikl equation for solving stress boundary value problems of elasticity. So, in the Lamé-Navier equation, we are having three equations involving three displacement components which are used for displacement formulation with the known displacement boundary conditions, whereas for the Beltrami-Mikl equations, we have 6 independent equations over 6 stress components, and those are used for solving the stress boundary value problems with the given traction boundary conditions on the surfaces. Now, while solving any one of these displacement boundary value problem or stress boundary value problem, we need to use various theorems of elasticity. So, in today's lecture, we are going to start our discussion on different theorems related to elasticity. The first one is called principle of superposition. This would be followed by the Saint-Venant's principle, then the uniqueness theorem of elasticity, the Clapeyron's theorem of elasticity, Beatty-Rayleigh reciprocity theorem, and finally the principle of virtual work. we are going to discuss all about all these different theorems related to elasticity one by one. So, first let us start with the first one, that is principle of superposition. Now, this is valid only for the small deformation problems and linear elastic solid materials, which are already our assumption for the infinitesimally small theory of elasticity. So, these assumptions are also valid or same for the principle of superposition for elasticity. Now, for a given domain R or within the total volume of the material, if we are considering one solution of the field equations to be sigma ij1, epsilon ij1 and ui1. So, sigma ij1 is first set of stress components, epsilon ij1 is first set of strain components, ui1 are the first set of displacement components, which altogether represents the one possible solution of the field equations of elasticity for a problem which is subjected to prescribed body force Bi1 and surface traction Ti1. Then we are considering another solution sigma ij2, epsilon ij2, ui2 as the second solution of the same problem, same field equation, but with a different body force Bi2 and a different surface traction Ti2. So, we are taking same body, same continuum described by same set of field equations, and then it is subjected to a first set of body force and surface traction as Bi1 and Ti1. With that, the corresponding solution is obtained as sigma ij1, sigma epsilon ij1, ui1. Then the same continuum is subjected to another set of body force and surface traction Bi2, Ti2. With that, the obtained solutions are named as sigma ij2, epsilon ij2, ui2. Now, the principle of superposition states that if you sum up these two solutions, so sigma ij1 plus sigma ij2 is the resultant stress, epsilon ij1 plus epsilon ij2 is the resultant strain, sigma ui1 plus ui2 is the total displacement. This one, the summation of these two individual solutions would be another solution of the problem if the combined body force Bi1 plus Bi2 and combined surface traction Ti1 plus Ti2 are acting on the same continuum. So, let us try to explain that with the help of one example. So, first we are considering this continuum, which is a square subjected to sigma 1, that is stress along the one direction, one is horizontal direction, 2 is vertical direction, let us say. So, this is subjected to one particular surface traction. So, Ti1 is specified here as sigma 1 on left and right faces, and when this body is subjected to this particular surface traction, the corresponding solution is obtained as, let us say, sigma ij1, epsilon ij1 and ui1, and we are not considering any body force. This is in absence of body force. Now, let us consider the second type of loading on the same body. So, that is the vertical loading sigma 2. So, surface tractions are applied on the top face and bottom face of sigma 2 intensity acting on different surface boundaries. So, that is basically Ti2 acting on the same continuum, and let us say the resultant stress, strain and displacements are obtained as sigma ij2, epsilon ij2, ui2. Now, based on the principle of superposition, if you add these two loadings, so if you are having a body subjected to sigma 1 along x direction, sigma 2 along y direction, and that same body with same dimension, the solution of the field equations of that problem should be same as the summation of these two individual solutions. So, if you add these two up, considering the body where both the surface traction T1 plus T2 are acting, then the solution of stress would be sigma ij1 plus sigma ij2, solution of strain would be epsilon ij1 plus epsilon ij2 and displacement would be ui1 plus uj2. So, this is nothing but the principle of superposition, and this is valid for small deformation, means strain displacement relation being linear, and for linear elastic solid means constitutive equation being linear, then only this principle of linear superposition holds true. Now, taking one example problem, let us consider one cantilever beam fixed at one endpoint O and connected to a vertical spring of stiffness K at another endpoint A. Total length of the beam is taken to be L and it is subjected to uniformly distributed loading of intensity small q. Now, using the principle of superposition, we can write this problem as summation of two other problems where two loads are acting differently, or we are having only one load acting on the body for each of those two individual problems. So, if you carefully observe, there are two types of external forces acting on this beam. One is the external distributed loadings of intensity small q, which is uniformly distributed throughout its length L. Another is spring force coming at point A, which is equals to k times displacement of point A, k times ua, let us say. So, we are considering the first problem where the same beam is subjected to only one loading, that is the distributed load of intensity q, plus the second problem where the same beam is subjected to only spring force Fs, which is k times ua, where ua is nothing but the deflection of the spring or vertical transverse deflection of that free end point A of the cantilever beam. Now, using the principle of superposition, the total deflection of point A would be summation of the individual deflection of these two different problems. In one case, it is deflection due to the uniformly distributed loading of intensity q, and another case it is the displacement of tip due to a concentrated load equals to the spring force of the system. So, ua would be ua due to small q plus ua due to spring force S. Now, E being the Young's modulus of the material of the beam and I being the second moment of area, we can write ua due to the uniformly distributed loading q as q L to the power 4 by 8 EI. These are known to you from the elementary undergraduate beam deformation problems. So, any beam, cantilever beam subjected to uniformly distributed load of intensity q throughout its span would be having end deflection of q L to the power 4 by 8 EI, whereas any cantilever beam subjected to a tip load at the free end of P would be having tip displacement of P L cube by 3 EI. Here, for the second case, that tip load P is nothing but the spring force Fs. So, ua for the spring case is Fs L cube by 3 EI. Now, Fs is once again related to the displacement u. So, Fs can be written as k times ua, spring constant times the displacement of the spring, compression of the spring. Now, ua equals to QL4 by 8 EI plus k ua L cube by 3 EI. Taking the second term towards left and then solving it for ua, the displacement of point A can be obtained as q L to the power 4 divided by 8 EI times 1 plus k L cube by 3 EI. So, using the principle of superposition, we can conveniently solve such problems where multiple loads are acting. We will be solving the same domain, same problem using individual forces, and then would combine the result of all those individual forcing cases to find out the total solution where all those loads are acting simultaneously on the same continuum. Now, moving to the next theorem, which is the Saint-Venant's principle of elasticity. This states the stress sigma ij, strain epsilon ij and displacement ui, all these fields caused by two statically equivalent force systems acting on the parts of a body which are far away from the region of interest of or region of loading are approximately the same. So, we will explain this particular statement through examples. So, let us consider a thin bar subjected to the axial compressive loading P at one of its end and another end is a built-in end or cantilevered. Now, here instead of P at this particular top point, let us apply P by 2 P by 2, two different forces of half of the magnitude of P at two adjacent points. So, instead of applying a single force P, we can apply P by 2 forces on two sides in a symmetric fashion, so that no moment is created about the central vertical line, about the central axis of the bar. So, moment is same and both the forces P by 2 and P by 2 magnitude forces are just a very small distance away from each other. So, then these two force systems can be called equivalent force system. Their effects must be same at the point of loading. Now, under such cases, when two different statically equivalent force systems are acting on the body, then if you consider any region which is far away from the region of loading, there we cannot distinguish any effect, any difference between these two cases, even though the loads are different but statically equivalent. Then if you consider any point which is far away from the point of loading, so let us say at the fixed support end of the bar, at the bottom point, the equivalent forces are acting on the top, we are taking the extremely different endpoints, the opposite endpoints, that is at the base. We would not be able to distinguish between the results at those two base points for two systems with statically equivalent loading. So, stress, strains and displacement fields would be almost identical at the base of both the systems when that base point is far away from the point of loading. This is called the Saint-Venant's principle. If you take another example, let us take a cantilever beam subjected to uniformly distributed load of intensity small q, fixed end is O and free end is named as A. Now, we are removing this fixed end O and replacing that with equivalent force V naught and equivalent moment m naught. So, this is a statically equivalent boundary condition at fixed end point O. V naught and m naught are so calculated that this first one, the given boundary condition, is equivalent to the second free body diagram. These are called statically equivalent boundary condition at right end point O for the beam, which is loaded with uniform load distribution of intensity Q. Now, if I consider point A, which is far away from point O, exactly at the opposite end of the beam, the stress, strain, displacement fields would be identical for both of these two cases with statically equivalent boundary conditions at O. So, for the Saint-Venant principle, it is basically stating that the effect of loading for two set systems which are equivalent to each other. So, for two equivalent force systems acting on a body, their effect would only be confined to the region near the point of loading. As you are going to the points which are away from that region, no difference can be felt in the stress, strain or displacement fields for the two cases which are having statically equivalent loading. Now, moving to the next theorem, which is called uniqueness theorem. This is saying that for given traction or displacement boundary condition and loading for the small deformation problems, the field equations of elasticity can have only a single unique solution for stress, strain and displacement fields. So, for any elasticity problem with a given displacement and traction boundary condition along with the given loading, with the assumption of small deformation, the field equations can have unique or single solution. We cannot have multiple solutions available for the field equations of elasticity. Now, we will try to prove that. First, we will violate the statement of the uniqueness theorem. Let us assume non-unique solutions are existing. Two different set of solutions are chosen. First set is sigma ij1 epsilon ij1 ui1. Second set is sigma ij2 epsilon ij2 ui2. These are the two possible set of solutions for stress, strain and displacements for the same elasticity problem. And defining their difference as another possible solution using the principle of superposition, which states if this is solution 1, this is solution 2, then their linear combination is another solution. This is the statement of principle of superposition. So, let us say difference between these two solutions is another solution of the same problem. So, sigma ij is equals to sigma ij1 minus sigma ij2, epsilon ij is equals to epsilon ij1 minus epsilon ij2, ui is equals to ui1 minus ui2. So, this different solution is defined to be another possible solution of the same problem, and for this case the Bi would be equals to 0, because the body force acting in first case and body force acting in second case must be same, because that is given. You look at the statement for given displacement traction boundary and loading. The loading means body forces, surface tractions, boundary conditions over gamma u and gamma t, they should be same for both problem 1 and problem 2. Thus, for the new state different solution Bi should be 0, as Bi1 is equals to Bi2. And Bi being 0, this new different solution must satisfy the boundary condition of this form, the equilibrium equation of this form sigma ij comma j equals to 0. In general, equilibrium equation is sigma ij comma j plus Bi equals to 0, but as Bi equals to 0 here, equilibrium equation reduces to the form of sigma ij comma j equals to 0. Similarly, they should also satisfy, the different solution should also satisfy the boundary conditions, which is ui equals to 0 on gamma u, the displacement boundary condition, and Ti equals to some given sigma ij nj equals to 0 on gamma t, that is fraction boundary conditions. Now, using the definition of the strain energy function, the total strain energy of the system can be written as volume integral of the strain energy density, and strain energy density is defined as half of inner product of sigma and epsilon. So, half of integral sigma ij epsilon ij over the entire volume. This is the total strain energy of the system. Now, we can write sigma ij epsilon ij as half of sigma ij times ui comma j plus uj comma I, using the strain displacement relation. Writing epsilon ij in terms of the displacement component, we can write this particular equation. Now, expanding it into two terms, and then in the second term interchanging the dummy indices I and j, we would be getting this. In the second term, we are interchanging I to j and j to I only in the second term. And then finally, in between this and this, we are using the symmetry of the Cauchy stress tensor, sigma ij is equals to sigma ji. With that, we can show that sigma ij epsilon ij is equals to sigma ij ui comma j. So, that is replaced here in the expression of strain energy. So, ut would become half of integral sigma ij ui comma j integral over the total volume. Now, writing this uij times ui comma j as sigma ij ui comma j minus of sigma ij comma j times ui. This is equals to sigma ij ui comma j. Why? Because if you just take this, the derivative of sigma ij ui, this can have two terms. One term is derivative of sigma with respect to xj keeping ui constant, another term is derivative of ui with respect to xj keeping sigma ij constant. So, thus this one term sigma ij ui comma j as can be written as the difference between these two terms. So, two volume integrals are coming, and using the equilibrium equation with 0 body force, for the difference solution body force B I is 0, equilibrium solution is equation is sigma ij comma j is 0. So, second term would go to 0, we would be having only one term. Now, using the divergence theorem, the sigma ij ui comma j integral over dv can be written as sigma ij ui nj integral over surface d gamma, and then grouping the terms within the integral into two parts, we can write total strain energy as half of surface integral of sigma ij nj times ui d gamma. Now, if you recall about the boundary conditions, on the boundaries we are having sigma ij nj to be 0 if the traction or stress boundaries are prescribed, that is on gamma t, or for the displacement boundaries, if gamma u is prescribed, we are having ui to be 0. So, on gamma t the first term is 0, sigma ij nj is 0, on gamma u the second term ui is 0. So, on whatever boundary conditions are specified, whether it is stress boundary or displacement boundary, either one of the term would go to 0, and thus overall ut would go to 0. The total strain energy for this different solution state is equals to 0. Now, if the total strain energy of this state is 0, the associated stress and strain components must vanish, because u is equals to half of sigma ij epsilon ij. U being 0, both sigma ij and epsilon ij components must go to 0. So, both sigma ij epsilon ij being 0 on the entire domain, and using the strain displacement relations, epsilon ij being 0, no strains are allowed within the body. So, body can only have some rigid motion without any elastic deformation. Now, if you use the displacement boundary conditions, at few points on the boundary, displacement boundary conditions are prescribed on gamma u, where ui is 0. So, ui being 0 at the boundaries and body having a rigid body translation only, rigid body motion only, we must have ui to be 0. So, we cannot have different values of ui within the body. Along the boundary ui is 0, then for entire body displacement ui must be 0. So, hence strain energy 0 refers to stress, strain and displacement, all of them to be 0 within the entire boundary. So, sigma ij, epsilon ij, ui all are 0, means the difference solution is going to 0, thereby resulting sigma ij 1 is equals to sigma ij 2, epsilon ij 1 is equals to epsilon ij 2, ui 1 is equals to ui 2. So, that means the two state of solutions, whatever we had assumed to be non-unique, they are coming out to be same. So, the elasticity problem or the solution of field equations of elasticity can have a single or unique solution, which is the statement of the uniqueness theorem, and thus it is proved. And moving to the next theorem of Clapeyron's theorem, this states the strain energy stored within a elastic body which is in static equilibrium is equals to half of the summation of the total work done by all the body forces and surface tractions acting on the continuum. So, let us consider a body which is subjected to body force B per unit volume, subjected to surface traction T acting over boundary gamma and velocity vector being equals to u. The work done by body forces can be written as this last term half of integral of B I u I integrated over volume. Work done by the surface traction force is written as this term, half of integral of T I u I integrated over the boundary d gamma, because surface tractions are acting over boundary, body forces are acting over entire volume. So, right hand side gives us the half of the total work done by surface tractions and body forces. And as per the statement of this Clapeyron's theorem, this should be equals to total strain energy stored within the body, that is integral of u over the volume, or ut, the total strain energy stored. Now, if you try to prove this, ut, total strain energy, is integral of the strain energy density function, volume integral of half sigma I j epsilon I j. And as we had already proved, sigma I j epsilon I j is same as sigma I j u I comma j, replacing that here within the integrand and then writing sigma I j u I comma j as sigma I j u I entire thing comma j minus sigma I j comma j times u I, same as the previous proof of uniqueness theorem. And then invoking the equations of equilibrium, the second integral term would become like this, because using the equilibrium equation we know that sigma I j comma j plus b I is equals to 0. So, thus sigma I j comma j, this term is written as minus b I, and in the first term, which was a volume integral, sigma I j u I entire thing comma j dv is converted into surface integral with the help of divergence theorem and written as half of surface integral sigma I j u I n j d gamma, where n j are the components of unit surface normal vector. Now, u t is equals to then half of surface integral of T I u I plus half of volume integral of B I u I. By using the relation between the surface traction vector T I and sigma, the stress component sigma I j, that is T I equals to sigma I j n j, that is replaced here, and thus this becomes T I u I integral over d gamma by 2 plus B I u I integral over dV by 2, and this is equal to total strain energy of the system. So, this is nothing but the statement of the Clapeyron's theorem. And in the vector form, we can write ut as half of integral T dot u integrated over the surface boundary plus half of integral B dot u integrated over the total volume of the material. So, in this lecture we had discussed 4 different theorems of elasticity known as principle of superposition, Saint-Venant's principle, uniqueness theorem and Clapeyron's theorem. Thank you.